So this meeting is officially being recorded. Okay, so just to give a quick reminder to all the faculty that are here now. So we've, sorry for the spam emails that went out, but we did fix the issue. So everyone's a panelist now. Feel free to turn on your video when you like so that the speaker can see your face, but do please keep yourself muted when you're not talking to the speaker. I think that's it for announcements. Other than to say we will be picking some students from time to time to be panelists for the colloquium.
And we would appreciate it if you could turn your camera on as a student such that the speaker can see your face.
That would be fantastic. Thank you, Serena. So today we are really excited to have one of our own giving the colloquium. So TimOhno graduated from the University of Maryland in experimental surface science in 1989 under the direction of Professor Ellen Williams, who coincidentally served as director of ARPA-E. So Tim's work at the University of Minnesota strengthened his interest in material science before coming to Mines in 1992. So in Tim's words, as the oldest member of the department, he has seen the growth of the department beyond its original research focus at the time, which did include photovoltaics. Leading that program led to service as the director of campus energy minor and ultimately support for student organizations involved in energy topics. So with that, I'm going to mute myself and hand it over to Tim. Tim, thank you so much.
No problem at all. I do have one question for one of the panelists. Chip is my compatriot as coming from the University of Maryland. But I also see from his background, he might be sitting in his new house. Is that true?
That's right. That's right.
So the true builder in the department actually is Chip. But I'll tell you about a student effort. So what I'm going to talk about today, let's see if I can get this running, was something which occurred almost exactly a year ago. I was thinking about this on Sunday, is the 1-year anniversary of this video that was made at 2 o'clock in the morning because the time zone differences was the end of the competition in Ben Guerir, Morocco. And this was the Solar Decathlon Africa. The Solar Decathlon, I'll explain in a bit exactly what they are. The goal of this is really to talk about the role of the physics department to a large extent, but also mines in general. There have been, from my count, about 15 Solar Decathlons, 8 in the United States, 3 in Europe, 2 in the Middle East, 2 in Latin America, 2 in China, and 1 in Africa. And actually, I take that back. The one in the Middle East hasn't occurred yet. They've only had 1 so far. To the best of my knowledge, we're the only physics department that's for sure led and won, and possibly even competed in these. It's an area that tends to be the realm of architecture departments or civil engineers or other groups. So with that in mind, what I want to do was lead you through a little bit of description of the entire trip, of how do we actually get to this point? What's the decathlon? What are tiny houses and how does this apply to that? And why do we go through that stage? And then more of sort of a storybook about the road to Casablanca, and then a little bit about what happened after. We're also testing out a new feature. So I'm going to launch a poll that you can vote in on. And this has to do with motivation for the Solar Decathlon. So in the United States, there are often 3 sectors, is the way we break things down. That doesn't include transportation. So if we look at commercial, industrial, and residential, whatever those mean, what's the order that you would have? George has a hand up, and I don't find the hand button.
Yeah, I saw that. I think you put it down. And I think we're not seeing the poll.
Oh, let me relaunch it. Here we go.
There we go.
Excellent. So again, the phrasing of the question to some extent is leading, but I want you to sort of vote what you think. And we're not going to spend a huge amount of time on this because it's either a reasonable guess or you know the answer. And again, you're only being graded on participation, just like Physics 100. Okay, I'm going to be pulling in a couple minutes, or a couple seconds, I should say. Okay, so we've got almost everybody voted in. So go ahead and click in if you haven't already. That's what I tell the Physics 100 students. And I'm going to end polling now. Okay, so these are the results that we had on it. That the leading category was industry, commercial, then residential. And again, you could do process elimination and eliminate some of these. Let's go ahead and take a look at the answers. Okay, so that's the only polling question that I had. This was really a little bit of an experiment, so that's great. Okay, so this is the answer. Now this is from Livermore Labs, and they have an annual compilation of energy consumption, both production and its uses in the United States. And you can see transportation is that big one at the bottom, and we'll talk a bit about that at the very end. The three other categories, industrial, commercial, and residential, if you look at the rankings on it, the majority opinion was correct, that industrial was the largest, but residential turns out to be the second. So for me, a little bit of a surprising thing, but again, it's somewhat categorization, is that residential is a big piece of our energy usage. The other part is if you look at the way that the different energy sources play into it, residential has a very, very large component, which is electrical generation and natural gas. So if we were to look in detail at electrical, in Colorado, the most recent results show where do we get electricity from. As was in that graph, electricity or residential uses largely comes from natural gas. And then when I look at the second category, it's now coal. It was not that many years ago that coal was the dominant source of electricity in the United States. Growing rapidly at the bottom is renewable energy sources, primarily wind, that you might have seen on the last graph. So this again has been sort of a big push to the current administration. Coal's dying, but it really is natural gas. The other thing to focus on is thinking about energy loss. Why was it, when I look at the last part of this, is that, whoops, that didn't work. Energy services is only a third of the total energy that was available. And so we see large energy losses that come from the production of electricity. But as that electricity flows into the house, we again see significant losses going past that, to the point that we see that this energy we consider to be so precious, we're concerned about it because of climate change, is about 2/3 wasted. So one of the things that we'd like to do is how can we actually modify this behavior, specifically in the case of residential. Now, if we look at the consumption of energy inside of a home, one thing we'll note is that it's dominated in all homes, this is US numbers, 2015, by space heating and by water heating. 43 plus about 20, so about 60 or 2/3 of the energy that goes into your house is related to heating. So that again leaves us a little bit of a dilemma, because when I think about renewable energy, such as solar and wind, it primarily is electrical. The solar decathlon was focused on these aspects. The solar decathlon started in 2002. And the picture we see here was actually recorded in Denver a little bit over 3 years ago. It's a competition, again, that occurs about every 2 years. As I mentioned, there have been about 15 total globally. And the idea in 2002 was photovoltaics was very expensive, is can we encourage the next generation of builders to think about how to incorporate solar into houses. It was intended, again, to be a little bit of a showcase. So in the case of the Denver, probably the most common visitors were school kids. And again, the idea was to promote clean energy. The decathlon in Denver, for those of you who had visited, you knew that it was outside of the Pena Station. So on the way to the airport by the Panasonic building was the site. And if you visited, you saw collections of buildings like this. This was a building constructed by DU as a local partner in the Berkeley University. This was by the University of Maryland, who've actually won once or twice. And this was a winning entry, which was from Switzerland. So the Swiss shipped this overseas, bought it back. The overall cost of the shipping and the construction of the building was about $3 million. So this was an issue with respect to the development of the solar decathlon. The other issue they ran into for the first time was the presence of snow. 2017, some of you remember the freak snowstorm we had. So a lot of the energy calculations that the students had done based on Denver climate were a little bit thrown off by this. The other presence at it, off to the sides of the lot for insurance reasons, was a tiny house. And so I want to talk about some of that as well. The idea of the tiny house was, if we didn't enter the decathlon because we're too late, was there anything that we could do? This is a group of students that started it. 3 of them are grad students. Some of you recognize material science grad students, Ethan Pillay and George Burton. They visited a builder of tiny houses in 2015. And the idea was, let's go ahead and take a look at one. For me as a physicist, the reason I think of this as being a good start is when I go back and take a look at the house that was submitted by Berkeley or by the Swiss. It's a very complicated structure, lots and lots of rooms, connections between pieces. A tiny house is a spherical cow. The physics idea of simplifying problems to the extent that I can try and get some insight into what's important and what's not important. So our approach in this, again, from a physicist point of view, was, can I make a simple structure as a lead into building the decathlon? Tiny houses have been sort of in the vogue. They've been around for a while. They're of the order of 100 to 400 square feet. There was no code associated with them until recently. In 2018 was the first code that was built into it. There are a lot of different applications. In Denver, some of you know about the community for homeless. There is some movement in things like ski resorts for making affordable housing. So again, they're of interest for different reasons, but for us, it's a good starting point. And the reason that the students put forward on this is we want to build a bigger building. So can we start with a pilot project? Can we try and look at building it for this climate? Since the 2019 decathlon should have been in Denver. Can we look at things which are maybe innovative and risky? And for the grad students, they knew that they probably would not be near the competition. Could they put the beginnings of what would go into a build in place for another team? So again, this idea was, let's do an experiment. Let's make a simple model, which is a tiny house, model the more complicated structure like DU, but it only has a single room. When I look at the way that air flows inside of it, it flows from one end to the other. Electrical wires run straight. Doing modifications on it was simple, and can actually measure and test things. So we started construction of this in 2016. So this is 4 years back ago. The students at the time thought this would be a quick construction, that by the time the solar decathlon came in 2017, they'd be done. That clearly wasn't true. To this day, we're still working on it, but these are some of the early stages of construction. It starts with the trailer, insulation, framing, and then walls. The person that I'm circling here is actually a physics major. Matt North graduated about 3 years ago and was one of our non-trad students, had a significant amount of construction background. He wasn't unique in terms of being a physics person on this team. There were 4 or 5 physics majors that were part. So now I wanted to get a little bit into the science part of it. I try and think about, what do I need to do to make a good house? And one of the parts which is important is heating and cooling. We saw from the plot at the very beginning that one of the important things that I look at when I look at construction is where did the energy go? and we saw that it was dominated by space heating and by water heating. Now to reduce those, I want to do the things that can make best thermal efficiency possible. One way you could do that is lots of insulation. A downside for tiny houses is that it's only 8 foot wide. So 1 foot wall would definitely be an issue with respect to a tiny house. So there are compromises to be made, and we can understand the cost of those by looking at modeling. Just an idea of the things that are available. Closed cell spray foam has an R value about 6.5. And I'm not gonna dwell too much on what these are. Bigger is better. So because they represent resistance. R is for resistivity to the thermal flow of flux. So there's different sorts of foams which are used for construction. Our house had this thing called a zip system on the outside, which is a continuous sheet. The inside was filled with spray foam. And we had a couple places where there was aerogel. Now, aerogel is maybe one of the first interesting applications of science. Everybody knows, and one of my other poll questions that we're not going to do is what matters in thermal transport in a house. We know that there's radiation, conduction, and convection. Is how do we eliminate those? It turns out all three are relatively important at room temperature, surprisingly. So radiation, somewhat true because when you look at buying strips of foam, they often have a reflective face on them. Fiberglass bats eliminate convection, but in the end, I'm still limited by conduction. The idea of an aerogel is suppose you can make little bubbles, so spacings where the sizes of the spacing is actually less than the mean free path of the gas. It turns out that the mean free path increases, the R value increases significantly. And so these were used in a few places, industrially used, not very often in houses. So that's our first model that we could determine and test inside the tiny house. Inside the wall are thermal sensors. We have both thermistors as well as the resistive semiconductor sensors that we use in field session. The other place where the science part comes into it is when you look at a complicated structure like the Berkeley house, is how do you add up all the different losses? You can model it, so there's several softwares that can manage this. But in physics, we want to do the round cows again. Is can I get an idea by looking at sort of gross numbers and get an estimation based on that? I could get the areas of the walls, the windows, the ceilings, the floors, and I can add those, but how do I add them? The science part of this is that the transport equations for heat are no different from electricity. So when I look at the behavior, the R values, the resistivities are added in the same way. Flow through the walls are in parallel, so they add as conductances instead. On the other hand, if I take a look at putting layers of different material, they add as resistances because they're in series. So taking this physics approach in mind is I can make an estimation of the amount of heat loss I would get if there's a 20 Fahrenheit difference between the inside and the outside. And it's about a couple hundred watts. And that again is an interesting number because when I think about how much heat I produce by just standing here right now, it's about 100 watts. What that means is for the tiny house, we've done a sufficiently good job of insulating it that we should be able to drive it on average with just a few bodies. Now, another way I can try and modify this behavior, because average isn't good enough, is can I try and modify the electrical equation by adding capacitance into it? Phase change material is an example of that. The closest approximation we typically have is thinking about a glass of ice. Is my drink stays cold because the latent heat of ice is relatively large. And so the temperature is retained at a very low temperature, close to freezing. If I could do the same thing at room temperature, then that would be a wonderful addition. Our tiny house has a large amount of phase change materials built into it. They're commercially available. So this image shows an example of somebody installing it on a roof. And we did the same thing. So the amount of energy we could store inside the house is about 6 kilowatt hours if we go through a phase transition. The amount of heat stored in just change in temperature is very small, but like the ice cubes, change of phase is a huge amount because of the change in entropy. So this is an example of thermal inertial, and we'll come back to that a bit when we talk about the decathlon house as well. The last thing is, again, going back to the heating and cooling issue, is how do I heat and cool and minimize the amount of energy that I waste? When we looked at that picture before, one of the challenges I had when I looked at things like cooking on an electric stovetop is I took coal and natural gas, converted it at a relatively low efficiency to electricity, transmitted that over hundreds of miles of transmission lines, resulting in transmission losses, brought it into my house through several stages of transformers, put it into my stove, converted it back to heat, heated up to a pot, and with the pot inside of it, the amount of heat going into heating my food is only about 15%. So there must be better ways of doing heating and cooling and running appliances. Mini splits are one way. Mini splits are heat pumps. The one that's in the tiny house has got an ability to put out, in terms of cooling, 3.5 kilowatts. And again, remember our calculation said that on average, we only needed about 1/5 of a kilowatt. So that should be plenty at that rate. In terms of heating, again, 4 kilowatts capabilities. So again, I should be good. What's important about a heat pump is, as we know from thermal, is that I can be more efficient moving heat from one section to another by providing energy than I can by converting that directly into heat. The COP, the coefficient performance of 4, means that in order to get 4 kilowatts, I only will require 1 kilowatt of electrical power. These are super important things in terms of thinking about house design. The last thing is ventilation. If I make my house drafty, then all my energy just clears out the window. So the idea of an ERV is, can I use a heat exchanger to try and minimize that? The one we have in the tiny house doesn't use very much energy, but it's not particularly efficient. But it's important because it minimizes problems in a tight construction of buildup of contaminants inside the house, including CO2. The last part is talking about the electrical on the system. I'm going to kind of go through this a little bit quickly because it's not running yet, so we haven't tested it. We have a unique design. There's PV on the rooftop. There's actually batteries on the rooftop as well as lithium-ion batteries on the inside. We're going to be running both an AC and a DC system, and the reasons for efficiency is tied into that as well. Panels are fairly standard. One of the challenges of the solar decathlon competition was it started as a competition for doing challenging things with expensive solar. But now solar is sort of a commodity. It's something that you buy and somebody installs. The modeling is the important part that the students did as part of this. So PV watts is one example. BOPT is another. And again, these rough calculations I can do give me a couple hundred watts. The more accurate calculations done by the students is up to 255. So my ability to do simple modeling and understand the way that houses use energy turns out to be fairly effective, at least for a simple house. So we learned a lot from the design and the construction of the house. We learned about thermal management. We should use heat pumps. AC and DC systems are good. There are a few things I didn't talk about, like the water usage and winter treatments. But again, the significance of this was that the goal was lessons learned in a simple model. Now in this timeline, when we started back in 2015 with the first visit up to the place in Lyons, and then finishing with visiting the solar decathlon at Pena Boulevard, the goal was we'd be set to enter in a couple months the 2019 decathlon. The problem was it was canceled. So this was communications we had with DOE. 2017, again, followed an election. And so a comment from another person was elections had consequences. DOE's budgets for renewables were slashed significantly at that point. So they chose to cancel it. Richard King was the father of the decathlons in 2002. His suggestion was look at a different place. So Solar Decathlon Africa had been launched about 4 months previous to this. And the idea of that was following the model of the Middle East and China and Europe is let's encourage international teams to build houses. Same basic ideas, 10 competitions, architecture through sustainability listed at the bottom, with a little bit less focus on energy than the original 2002 competition. We would build for 3 weeks, we'd compete for 2 weeks, and this would happen over about a year and a half. Part of the focus was to be unique in the sense that it emphasized the idea of African culture. This competition had 18 teams in it. 20 is kind of atypical. There was only about 11 at the Denver competition in 2017. Morocco was a nice middle ground to choose. It's not extremely hot like portions of Africa. It also has a need. If you look at Morocco, it's not an oil producer, even though it's part of MENA, Middle East, North Africa. Its production of fossil fuels is very, very low. Their emphasis has been on solar thermal. Lots of sun, so concentrated solar power was an emphasis for them. They have good solar exposure, so the equivalent of 3.5 kilowatt hours per meter squared per day on an annual average. And the government, which is a monarchy, there's a king in Morocco, had taken a position that they were going to focus on renewables. Ben Gurir was the location of the equivalent of NREL. They had a number of institutions, governmental, that were launched. So Ben Gurir is in this location. Marrakesh is below it. Casablanca is above it. Both are separated about an hour, hour and a half by train. The site of Irisen in Ben Gurir was a reason for its location there. The other reason is, in addition to Irisen, in the far background is a university, UM6P. The M stands for Mohammed, the current king. Every king has a university. And so his flagship was this location in a relatively small town. So our goal was to think about entering that competition. The students answered with a resounding yes. Many of them would have graduated before another US decathlon happened. So we decided to try it. And again, keeping in mind that a physics department has never done this before. Now, the one thing that worked in our favor is we actually knew somebody in Morocco. One of the largest universities there with 42,000 students on the main campus, but it's a collection like the University of Colorado. So in its system are over 100,000 students, was Qadi Iyad. Qadi Iyad was in Marrakesh, so it's about an hour and a half away. One of the graduates was one of the first people I met at Maryland. I'm sorry, not at Maryland, when I came to Colorado. John Trefney, who some of you know through the Trefney Center, was the department head at that point. He had a student that graduated within about a half year. He was actually in the very first class I taught here. When he graduated in '93, he took a faculty position at Qadi Iyad. He's now a full professor, although his expertise here was in low temperature physics, not the Ely low temperature physics, but low at that time. He transitioned to looking at thin film science. So as a member of the physics department, he was the first call we made at that point. Within this department was also a physicist who was trained at McMaster's in Canada, who was a specialist in building science. And then the last partner that we added later, about 6 months down the road, was a civil engineer. But again, the uniqueness of this was we had 2 physics departments that were the leads on a competition that were primarily architecture and engineering. Our team started with 2 architecture schools, kind of recognizing our weakness. There was a university in Torino that we knew through a different connection. And in Morocco and Marrakesh, there's a university, ENAM, the École Nationale Architecture Marrakesh, which was there. Our team started relatively small, 7 students from Torino with 3 faculty members, shown here. Mine's had a large group, which originated because we started with a tiny house team, and 3 faculty that expressed interest in doing it. Qadi Yad had 2 faculty at that time, later expanded to 3, and 3 grad students. A branch of Qadi Yad, ENSA, had 10 students that attended the first meeting. And then ENAM, the architecture school, had 3 students and no faculty member. Unfortunately, to the end, they did not have a faculty representative. Things happened pretty quickly after that. In 2 weeks, we wrote a proposal. For those of you who written proposals, that's lightning fast. We were accepted into the competition a month later. I flew out with Lucy, who at that time was actually in Europe already on a study abroad, to the first meeting in the first week of May. We started having deliverables due during that summertime. And from the start of that until the end of the competition was a very, very short period of time, only 16 months total. At this point, we actually had only $50,000 from the competition. Now, what did mines look like at that point? The number I sort of want to highlight here is the 5 physics majors. But we had breadth. We had electrical engineers, which was great, mechanical engineers, a few civies, and students from other departments. The other part that's notable, though, is you take a look at the distribution across the undergrad population, as well as a couple of grad students. The first thing we need to do is raise money. We approached President Johnson and the deans at the time. This was part of the presentation by the students. What they were trying to do is get an idea how much things would cost. You recall I mentioned that the Swiss house was several $1,000,000. And theirs, of course, was complicated because of transportation costs. But we were at least making the one-way trip to Morocco as well. The estimates that we had were that we could pull this off using donations and local materials with a much, much smaller amount. At that point, we had raised $80,000 from different forms of competitions and by donations, but we thought we'd need more like $250,000. Some of these could be arrived by different ways, but the ask was $50,000 as well as other things. So this again is a big project from a mines point of view, having never done anything like this before. So the things we requested and needed at that point, and again, the big one was this, is can we get money? Because we already had about 80,000 and we're looking at about a quarter, including donations. And could we get space? So amazingly enough, we were able to get all the commitment financially from the university, and some of the other things started to roll in. So as you know, since I'm talking a year later, we succeeded at it. So I want to tell you a little bit about the house in the time that remains. Because of the focus on Africa, one of the things that we want to do was be aware of local materials and their impact on sustainability. So these are examples of things that went into the finished product. I should say they weren't necessarily the things that we designed into it. So the design process was very iterative as we learned what was available and what we can get for donations. We had reeds in the ceiling. We had tiles in the base that were fired locally and tiles in the wall that were not fired. And these were weighing into account the energy impact. So if you do energy analysis of the different building materials over time, one of the surprising things that came out of it was that lumber turned out not to be a bad choice. Morocco has almost no trees. So in the analysis of the sustainability materials, you take into account the transportation costs and the disposal costs. Concrete turns out to be fairly poor because of the amount of CO2 it produces. So our emphasis in this case was we started changing our original idea to something which is local, and that's compressed stabilized earth blocks. Their big advantage is they're basically dirt, 95% earth with a small amount of Portland cement, and they can be designed to be load bearing. So again, this really influences the way that the students did the design in fairly creative ways. Now we had a partner from the US that was going to provide these. That was part of the 10,000 donation, is that our walls would have been free, the structural materials. There are worldwide a lot of efforts, primarily in Malaysia and South America and India, in the idea of these compressed earth blocks. The intent on them, again, is to reduce the amount of Portland cement, but get a structural element, but also make construction fast. So these are Legos with the thought that, can I go ahead and construct a building with Legos? I can make it fast, and these openings inside of them can be stabilized by putting structural supports inside of them. There is a company in Boulder called Colorado Earth that does this, and that all sounded pretty promising with respect to our approach on it. So this is an example of a machine that was going to be shipped in by the American company to Morocco for doing the construction. Now, I mentioned before the idea of the aerogels. Aerogels are not common even in the United States. But what the earth blocks do is they add thermal mass. So if I think about electrical systems again, is I've added capacitance into it. And if I think about what I've done electrically, is my outside temperatures fluctuate tremendously in Africa, is what I need is I need a low pass filter. And for a low pass filter, I need both resistance, insulation, and capacitance or thermal mass. So the design the students did, which was considered to be sort of crazy by the builders that we're working with, was to do alternating layers of earth blocks on the inside, insulation in between, and earth blocks on the outside. So again, electrically thinking about that, that's a series combination of two resistors and a capacitor with a shunt resistance inside of it. So that again seems kind of promising. I should mention that Colorado Earth, the house they built in Castle Rock, does not follow this principle, but they've since switched to this design idea. So they are going to continue to look at this as a possibility as well. There was a senior design project in the physics department based on this. It focused on the idea of making air quality good. Rather than have an ERV, which we have in the tiny house, it had a CERV. The primary difference with the CRV is it's got monitoring built into it. So it detects CO2 levels and monitors air quality, as well as volatile organic compounds and other things. And it's got a heat pump. So rather than relying on passive means of transferring it, which I know are ineffective, is by adding a small amount of energy into it, I can actually move the heat 100% from the outgoing stream to the incoming stream. The other part of the project was control systems. Tristan de Bruner, who some of you know from classes, was the designer of this. It was a completely home-built system, sort of a hobbyist's Alexa or Google Home on steroids. So very, very sophisticated sensors built into it, that it is a part of his 317 project. Okay, so the design, again, combinations of the original idea, which came from the American team that wrote in 2 weeks, and upgrades based on the Moroccan partners, was these earth blocks with an opening in the middle. So the intent was Moroccan buildings are primarily designed around open spaces. So riads typically have a center opening. Our buildings are too small for that to happen. And so rather than having a center of the building, we had a courtyard. Space-wise, at 1,000 square feet, which is a competition limit, we were able to fit all the things in that we needed. There are a lot of challenges in this, and I'll show you a little bit about the progression designs. One of the downsides of this was we had some disagreements with the architects from Italy. So one of our early challenges was we lost our architects, at least one of them. Much like with the tiny house, we did modeling on it. So we were taking a look at the impact of different parts. This is hot water and heating. The thing to note about that is that represents only about the top quarter of our energy consumption when we did the modeling. And recall when we looked at the US energy consumption on the early slides, that was about 2/3. So the design of the house was such that we had an improvement of a factor of about 3 with respect to that. Some of the challenges in this are ones that we have uniquely as Americans, is the fact that we deal with English units and everybody else deals with metric. We didn't have any NASA type disasters, but there were some definite issues as we're going through the construction. Materials were not available there that were used to being here, and I'll mention some of those later. Things like standard timbers. There are no 2x4s in Morocco. So these were things that had to be taken into account as part of the construction process. Now the evolution, starting from where we submitted a design after a 2-week design process, started with the U-shape and PV on the building in kind of a little bit of a cartoony construction. Our first design with the Italians had a wind tower on it. We did modeling in the physics department on the idea of capturing wind drafts to do cooling in the house. And it turned out that wasn't effective. We looked at the actual meteorological data for that area, and we couldn't get enough benefit at the cost of actually introducing extra air into the house. The evolution led to a covered courtyard, different apertures around the outside of it, reorientation because of lot changes, until the house that we finally had when we went over to do the construction. So what did we build here? Whoops, I need another device. Oh, here we go. Apparently the pen doesn't work. Let me try this again. Okay, for whatever reason, I can't get the videos to fire, but no big deal. So there was a water well that was built in Brown Building. We constructed that here because it minimized the construction time on that end. This is the group of students hauling it out past the Brown Building. We had to ship all of this over there. So Fred is familiar with all the issues tied in with that, as well as Lawrence. We had a shipping container go over there with 2 months to spare. And one of the difficulties was we had no place to actually land the shipping container on that side. So in the container, though, was the water well that we constructed, windows, doors, solar panels, insulation, constructed wetland, and other hardware. So we crossed our fingers, hoped there wasn't any disasters in the Atlantic Ocean, and that would arrive before we did. Now, here are the challenges we ran into. So I'll spend the last little bit talking about the house, but I just wanted to mention that things don't always go as planned. The first thing we discovered was that the bricks that we'd been promised, the $10,000 donation, were not available. There are some custom issues, some other problems as well. In July, we found that we had no walls. So that was a bit of a problem. We scrambled and were able to find bricks over there, but involved a complete redesign of the house. The wall structures and the support are different because we had to re-engineer them. We had lost luggage. Our shipping container was tied up in customs for 3 weeks. The batteries, which are shipped separately because they contain lithium and are energy containing, did not arrive on time. The foundation that was constructed by the competition runners was not correct, and the water and the electricity were in the wrong places. Probably a more severe one was we're all used to Home Depot and being able to do constructions based on that. There are no Home Depots. We expected that. What we didn't expect was that in a small town like Ben Greer, there are no credit card transactions. Everything is by cash. There are many materials like gutters that are not available. The one which had an impact on us was there was no ABS plastic cement, and we shipped over our drain lines uncemented. So these are just examples of things that we ran into as problems going over. We did eventually buy 7 truckloads of bricks and started building our walls. It was not very well set up. The site didn't have potable water for drinking much, except for one building. It didn't have restrooms. It didn't have places to sleep or take breaks. So over that period of time, Tristan again is our physics major, Jeremiah's from mechanical engineering, and Christian is an EE. We launched into doing the walls. And we also ran into weather issues. So again, for whatever reason, my video is not going to run, but I'm not going to worry about it. Dust storms and rain. So typically the area is very, very arid, and the weather at that time of the year is very flat. Effectively 40 degrees or higher for the entire time. 40 degrees Fahrenheit, Celsius or higher, 110 Fahrenheit. But we actually had a dust storm that rolled in and wiped out a half a day. And we also had rain on one day. So these were, again, other challenges of the construction, which, again, was being built inside of 3 weeks. Construction was challenging. So we spent half our time building the walls. This was brick by brick, almost completely students. We had 4 masons we hired at $20 a day. And we had an army from the Moroccan universities of about 40 students that we ran in 3 shifts. So we had 6 Americans over there, and we were able to complete the walls and lower the ceilings. So this is a few images of what the house looked like on the inside as we're putting it up. This again is Tristan installing the CERV, the high-tech ventilation unit, and different pieces going into the house. I have a few images coming up later, but I just wanted to mention that this idea of the opening with the privacy cover on it was really a driving feature of the house. The pergola on top of it was mechanized, was our innovation on it. So we could take advantage of the weather on a given day. A few quick things, and I'm going to stop to the last ones. We don't have a full set of data, but during the competition, we had a connection that we could see both the output of the ventilation system. This shows that it maintains temperature. And this shows that when the CO2 content went too high, it actually switched on to redistribute air between the inside and the outside. We had a sophisticated battery system. Again, it didn't arrive on time, but the intent was to reuse car batteries. We did some modeling on the PV. The panels we had, and again, PV is less challenging than it used to be. The main panels on the rooftop were a result of an interaction with a physics major who now worked at SunPower, and people we knew from NREL that had started a company in China. So we had some panels that were transparent and some that were standard. And so this is visually what they look like. Rooftop solid panels and 70% transparent panels for the patio. Okay, what I wanted to jump to in the last minute I have is what happened. So we competed in this 10 competition trial over 2 weeks. We finished first, but we didn't finish first in very many categories. What we did best as engineers was energy balance and innovation. What we did worst at was architecture. But we did very, very well at a couple other categories, such as market appeal. So I think it sort of speaks to the creativity of students from Mines. There are a number of things that we learned on it. What I wanted to do was talk about in my last 30 seconds is where did students go? So what was the benefit of doing this competition? Katie Schneider, who was the E-Days engineer of her year, was not able to make the trip, but she did make it there in November. She was invited over as a speaker by the US Embassy to present at a celebration of a joint moonshot project between Morocco and the United States. So she presented to a group of students. She's since moved on and is working at a patent company up in Boulder, along with, as it turns out, 2 other physics majors that many of us know. A driving factor in her turning away from a career with aerospace. She had offers from both Lockheed Martin and from Raytheon, from Northrop Grumman, was the decathlon. Talking about science, doing management, and discovery, learning new things was something that was part of this experience, which is unique to physics majors. Lucy Davis is now in Portugal, probably one of the few Americans who have chosen to travel because she had an Erasmus. So she right now is looking at structural design for historical structures, and she'll be there for a year to get her degree. This again was driven by this project. Michael Blonsky, some of you may know from Mineral as a grad student, originally started in power systems and has now switched to residential as a result of this. Taylor is sitting in the audience and is working on quantum information systems. So not a tie-in at all, but again, love having him. And Tristan is now a software engineer up in Boulder. For me, I came back and there was a group of students that placed second in the Solar District Cup. We started in October, so 2 months later than everybody else. I retired my steel toes. I bought an electric car, and that's sort of led to thinking about the last couple things. So I just wanted to mention that although we were unique in being a first physics department, you can see how science couples into all of this. And so then questions are, where do we go next? And what are future directions that physics majors or engineering physics majors might tackle? In the house was a CERV. It's too expensive at this point, but I expect they'll become standard at some point. The latest model actually has a UV unit built into it for disinfecting. So their advances continuing, and these price drops will be important for that. Bill Mulligan, who is at SunPower, is moved on to another company where they're looking at modifying the matrix, which is graphite in lithium batteries with silicon-based materials. And the goal is to drop the price. There was a recent announcement by Tesla about shooting to drop the price of solar cell of batteries tremendously. 2 years ago, we had a speaker who talked about the idea of chemical noses, is can we do control systems that would be based on trying to do science with these are microstructures elements with chemical interactivity built on top of them. Better walls. So a vacuum panel, this is representative what our insulation could be, because the best reduction in thermal conductivity is the absence of particles. So Oak Ridge is actually looking at these and producing them right now. So this has only occurred in the last little bit. And then there's a company which is spun off of a mechanical engineer in Boulder that's looking at making a micro-engineered film that couples with the sky for doing cooling. These are kind of the ideas of things that people are looking at in the physical sciences that could build into building science in the future and future solar decathlons. Okay, so for that, that's kind of the end of my presentation, and I'm open to questions.
Awesome. Tim, that was amazing. So I think we have a question. I don't know if you can see the Q&A little menu at the bottom. So if you want to go ahead and.
Sure. One of the things which is going to be interesting looking at transportation, on the graph, it was actually the largest energy consumption of all, not just our personal movement, but also shipping of different sorts. So it was almost half of the energy consumption. When we go from internal combustion engines to electric vehicles, there was a point where it didn't make sense to drive an EV in Colorado. And that's because we made our electricity from coal. About 4 years ago, we actually crossed that threshold. So for 98%, I believe is the latest numbers from the Union of Concerned Scientists, it makes sense to drive an electrical vehicle. Now, in terms of consumption of energy, though, that's a behavioral change. Things are modified a bit right now. People with electrical vehicles watch very carefully their gauges because the ranges aren't big enough. But I think that's going to change. The other place that EVs will change is there's a big effort right now to make the millions of batteries that are going to be driving down our roads part of the energy solution for the entire grid. is with smart systems, you can imagine that when everybody parks their car during the middle day, that they could be charged. And then at nighttime, the batteries could be discharged. There are a lot of efforts looking at smart systems to incorporate the batteries that are inside of the EVs as part of the whole grid. So that doesn't answer very well, and partly because I think nobody really knows. Colorado is making a big push in that direction. So shortly you'll be able to charge your vehicle going up and down I-70. Alan maybe has a planted question. His question was about dust accumulation. If I were to fix anything on the house, the one I would fix is the student should design a panel cleaner. Because it's a desert region with lots of dust, we had a huge problem with dust accumulation. We were losing probably 30% of power production. So during the competition, you notice we won the energy competition. We were climbing on the roof every day to wash the panels, at least for the first week, until we're banished because of safety violations. There are ways of looking at cleaning dust. There was a project in Saudi Arabia that was doing this for concentrated solar, because it has the same issues. Is they have huge reflectors for concentrating solar to get heat, but their issue again was accumulation. It's a problem because it's also distinct to the region. If you're in a solar region, the accumulation is salt-based. If you're interior, it's primarily dust, and the means of removing it will be different. So our answer was, we messed up on that. We did not handle it all, but for the next group that competes in Africa, they definitely should. The semi-transparent cells, if you look at the performance based on the area, they were equivalent of most CadTel solar cells that are kind of in the middle range. So their efficiency was 15 or 16% for a commercial product. Record cells in CadTel are higher. Some of the new modules are a little bit higher than that too, but that's pretty decent. But again, you eliminate the bulk of it to allow light through, so you lose that. I should mention the reason that we had two sets of cells besides aesthetics is that because our house was actually not facing south, we had cells that were facing southeast and facing southwest so that we can capture sun over a bigger window of the day. If we had more time to redesign it, probably the porch would have had a combination of opaque and semi-transparent cells. To what extent are the techniques scalable? Some of them are more scalable. The CERV, the HVAC management, works much better with multi-family units. The earth blocks are limited in how tall they can be. One of the limitations is earthquake zones. Our original design had rebar running through the openings in the brick. Our new design, the walls were 40% thicker because they had no rebar. And it also meant they had to be shorter. A second floor is not possible for these. So in that case, it's not scalable. The, let's see, which other ones? I guess the solar and the air conditioning and the materials are the ones I think of offhand. I'd have to think a little bit about some of the other features. Okay, so I got a 215 question from Nicholas. Is there a thermal equivalent inductance that I could use? I cannot think of a thermal equivalent of inductance. Nope, can't think of one. Resistance and capacitance is it for me. Just as kind of an aside on that, going back to the electrical geeks in the audience, there was arguments from the Moroccan side that we actually didn't need air conditioning because of the thermal mass. That turns out actually not to be true. And there's an electrical answer for that as well. The electrical answer is that the fluctuations between the outside air and inside air are eliminated by the resistance capacitance combination because it's a low pass filter. But if you look at the steady state solution, not just the transient, or you look at the transient solution as well, the DC offset at the outside temperature will eventually creep on the inside. So you require both the DC and the AC solutions. And as a result of the DC part, eventually the average temperature on the inside will actually raise to the average temperature on the outside.
Interesting. So Todd wanted to point out that I think some folks, so Matt North is still building tiny houses in Boulder.
He is.
Just different types, apparently. So
yeah, he's converting vans into campers.
Yes, I could believe that. Actually, he had emailed me a while back to ask about ampacity versus amp carrying. This is, I think, one of the areas that if mines were to ever do this again, we need way more electrical engineers and civil engineers. Questions like ampacity are beyond my scope.
that is awesome. Well, I think we're just out of time here. So Tim, that was such a cool talk. Thanks so much. I learned a ton, and we're really thankful that you were able to take a little bit of time out of your schedule and give this talk for us. So I think
No problem.
With that, I think we are able to go ahead and wrap things up. What do you think? Yeah. Yes. Thank you, Tim.
You're welcome.
Awesome. All right. Well, thanks everybody. And we will see you again next week, same time.